Hello, my name is Mela Coffey. I'm a PhD student in the robotics lab at Boston University, and I'm excited to present to you our work on safe collaborative teleoperation of ground robots. Now, just to give a little motivation behind our work, I think it's safe to say that most robots and automated technologies commercially used today are designed to work for us instead of with us. And as such, most robots that are made to interact with humans, like teleoperative robots, do not truly collaborate with the human user. To address this, we envision a collaborative personal mobility platform, such as a powered wheelchair, in which the human user is responsible for making high-level navigation decisions about where to steer the robot. And in turn, the robot provides haptic feedback in the form of force feedback to provide collision avoidance and route planning suggestions. And this allows for collaborative teleoperation, or this co-navigation between human and robot. On the right, here's a preview of our proposed algorithm in practice. A human user manipulates a haptic device to steer a robot through a cluttered environment, and force feedback is provided to the user that pushes the user's hand in a direction that steers the robot into a safe position. Our work falls under the umbrella of haptic shared control, where a human operator receives feedback to maintain safe operation of the vehicle. In cluttered environments, haptic feedback is useful for collision avoidance, such as the one on the left, where feedback encodes a repulsive force from obstacles. However, these approaches don't help the user maneuver around the obstacle. So recent work has added the haptic guidance along planned paths to address this, like the study on the right. However, these and other prior studies have not fully explored haptic feedback for safe co-navigation of non-holonomic vehicles. In contrast, our work implements collision avoidance and guidance to the user's target while providing an in-depth mathematical performance analysis of our approach, with detailed simulations and human demonstrations. So in this paper, we present a haptic guidance algorithm for collaborative teleoperation of ground robots, which combines two components of haptic feedback: collision avoidance and obstacle avoidance. Collision avoidance helps steer the robot away from obstacles, while obstacle avoidance helps steer the robot towards a suggested safe path around obstacles. We propose a non-holonomic RT star-based path search for the obstacle avoidance portion of the haptic feedback, and we present analyses of the proposed algorithm to guarantee collision avoidance with obstacles. And finally, we present simulations and hardware experiments with virtual and human pilots. So let's get into the details of how we generate the force feedback. Here we consider navigating through a 2D environment with circular obstacles. And as the human steers the robot, we predict the user's intended path for the next t seconds. If we predict that the user's current steering direction will cause the robot to collide with an obstacle, then we provide haptic feedback. As mentioned, our haptic feedback has two components: obstacle avoidance feedback and collision avoidance feedback. And the collision avoidance feedback is always outward normal from the obstacle to help push the robot away from the obstacle. And we scale the magnitude of the force depending on how close the robot is to an obstacle. So the magnitude increases as the robot approaches an obstacle. The obstacle avoidance force aims to push the robot onto a suggested safe path and help the user maneuver around the obstacle. And in this paper, we propose a non-holonomic RT star-based path search algorithm to generate a suggested safe path. To do this, we search the local space around the robot and use a non-holonomic RT star algorithm to search for a path from the robot pose to the predicted goal pose within that local space. And once we have a safe path, then we can generate the obstacle avoidance force, which points toward and normal to the suggested safe path. We also scale this force depending on the distance to the path. So the farther the robot is from the path, the greater the magnitude. Then we can compute the total force feedback as the sum of these two forces multiplied by constant gain, which scales the magnitude of the force feedback and can be tuned to the preference of the user. And now I'll get into our simulations and hardware-in-the-loop experimental results. Starting with simulations, here's an example of a robot navigating from the blue starting position to the red goal position. Here we use a simple PD controller as a virtual pilot, and its only purpose is to steer the robot to the goal location, and it has no information about the obstacles. So ultimately, the only thing that can steer the robot away from the obstacles is the force feedback. You also notice the green curves, and these are suggested safe paths for the user to take, and they're used to compute the obstacle avoidance force. The simulation you see here is just one of 100 different simulations we ran, and we found that over all 100 trials, the robots were able to reach their goal and the robot never collided with an obstacle. We also used the same environment you see here in hardware in the loop experiments. First, we used a virtual pilot with a unicycle robot, the JetBot. So again, the virtual pilot just steers the robot from the start pose to the goal pose, and the haptic feedback is used to steer the robot around the obstacles. And then we performed 3 different experiments with a human pilot. In the first case, a human experimenter teleoperates the JetBot with visual feedback only, so without haptic feedback. The human has a third-person view of the environment and steers the robot using the Geomagic Touch haptic device you see in the bottom right. In the second case, we allow the human pilot both visual feedback and haptic feedback. So the setup is the same as the first case, but here we provide our proposed force feedback. And in the third and final case, the human pilot cannot see the obstacles and instead has to rely on our haptic feedback to guide them around obstacles. We show the animated version of this case in the bottom left, where we can see that the human is able to steer the robot and avoid all obstacles. And here's a summary of all that I just showed you with the force vectors shown along the robot trajectory. From these results, we can see that our approach allows the user to avoid obstacles while still reaching their goal. And we can see that the feedback is not always active, which provides the human with more autonomy and creates a collaborative navigation paradigm. Finally, I'd like to thank everyone here for listening and feel free to contact me about this work via email.